All right. Hello, everyone. Thank you for joining us for our next talk. It's called An Alternative to RISC-V-based zkVM's AI-based transpiler with Fuzz, Diff, testing. A lot of words there. We're going to get it all broken down for us. Please welcome to the stage Elias Tazartes, co-founder of Kakarot. Yep.
Hey guys, can you hear me? Okay, all good. So my name is Elias. I'm one of the co-founders of Kakarot. Funny story, Clement, my co-founder, was supposed to be here today, and he just had a newborn, so congrats, Clement. So I'll be doing the talk. We're both engineers, and this is kind of the newest framework or dev framework we've been building in the last 2 months, surprisingly, because AI moves so fast. So I'm going to just define quickly why you would want to have ZK, just to get us on a playing level, and then investigate how you go from just any software to provable software. So why you would want ZK, especially in verifiable computing, mainly for cheaper verifiability. So blockchains, as you know, are verifiable compute engines, and I would argue that the most important thing that defines them, or like characterizes them, is the ability for anyone to come in, become a participant of the network, and convince themselves with sovereignty that the protocol is operating with integrity. So this is what we call verifiability. And ZK provides us with a new way to have verifiability that is cheaper than the former way, which was re-execution. It's broader because it requires less compute, and it gives you good interop because ZK allows you kind of to mix and match many data sources, whether it is your passport, on-chain data, off-chain data. So that's why you build provable software, to have verifiable compute and have more eyes, or like I would say sovereignty on the results that you expect from digital economies. And today we're going to talk about how to transpile code from a normal code base, whether it is in Python, Rust, Go, to a state where it is provable. And I would like to remind everyone that I think one of our core values, but I think a value that lots of people share, is that you don't want to write code. So the less code you write, the better you are off. And I think this is what leads most of the changes in the space for the last year. So imagine you have a software, and let's take the EVM, because this is one software that we're very familiar about with at Kakarot. It is the execution engine of the Ethereum protocol. And so it is written in many languages. It's a piece of software. It's written in Golang. It's written in Rust. It's written by many people in different ways. And you want it to become provable. What it means to be provable is that any execution, any run that you do with this virtual machine needs to be able to generate a ZK proof, a zero-knowledge proof, which is essentially a certificate of integrity that your software run was done correctly, or obeying some constraints. So you can do it 2 ways. You can write circuits, which is this mathematical kind of applied computer science construct that allows you to define constraints. It's very low level. It's akin to assembly. And I would not encourage teams to write it because it is very time consuming and resource consuming. The other way to do it is you just take the code base that you have today, which you have already written in Rust or Go, etc., and you compile it down to ZK, so to an instruction set that is provable. And this is what we call RISC-V-based zkVM. And there are others, but this is the main paradigm that occupies people's mind share. So this is how we kind of see it: is write circuits. It takes time. Most teams that have been writing circuits in the last years are either very specialized or switching to zkVMs. And so it's too long to write circuits, too hard to audit, too tedious to maintain, and it's for the few. There are a few teams that are doing it, but most people are using zkVMs. So you choose an instruction set, RISC-V, WASM, MIPS. Who here has already heard about RISC-V? So many people. And so RISC-V has gained a lot of mindshare in 2024, mainly because it's performant enough, and it's so fast to go to market with it, because you have a code base, and you just make it provable in less than a week. So this is just what you want when you're a team. You want fast go-to-market, cheaper audits, because less code, and maintainability. So as much as blockchain space changes, you need to adapt. Ethereum, we started the analogy of Ethereum, or taking it as an example. Ethereum hard forks or upgrades its protocol once every 6 months to a year. When you write circuits, it's very hard to keep up. So RISC-V won a lot of mindshare. Many languages can compile to RISC-V, you have a stable toolchain finally, and you have good enough performance. So is there any other way, or is this the end, is this the end state? Is this the kind of the space has matured enough so that it doesn't need to change anymore? And to some extent, circuits are no longer, I think, the choice for teams that want to do cryptography. zkVMs are. But there are many ways to go about zkVMs, and this is what we're going to explore in the remaining 14 minutes. So what's a zkVM? I think if you really go down to the essence, a zkVM is simply a VM, so some kind of computer, for which execution can be proven. And this is very powerful when you think about it. So far, what we were able to do was maybe prove theorems with formal verification, but we have never been able to link a code base with a result. So you've never been able to link, to be able to say, this result that I've that this algorithm fed me is the correct execution of this algorithm. Today, you have to either trust who is giving you the results, so whether it is an AI system or any kind of blockchain, when you connect to a RPC, you trust that they're giving you the right result, or re-execute. And this is what nodes in the Bitcoin protocol or Ethereum protocol do. They just don't trust, they verify. And the way they verify is that they re-execute every single transaction in a block. And that's very costly. So a VM that can be proven, and that a VM is simply just an instruction set. So it doesn't mean just RISC-V or WASM, it means any instruction set that can run Turing complete, like any type of app. So that includes Cairo, Valida, Maiden. So maybe just to show of hand, who here has heard of Cairo in the past? Yeah, so half of people. So just prove an instruction set. So what's the trade-off? What instruction set gives you the best performance, but is easiest to master? So if you have a product, how fast can you make it provable and still be performant? Is it 1 day with RISC-V? Is it 1 week with Cairo? Or is it 1 year with circuits? And we call ZK native an instruction set that is made to be proven. So RISC-V was made to be broad, was made to be very simple to compile from Rust to RISC-V, but it was not made to be proven. It is a very fortunate, good convergence point that is easy enough to prove. So what if we could transpile a code base, like a Rust code base, a Golang code base, to Cairo assembly really fast? Like what if we could bridge this gap, the whole spectrum being 1 year to write circuits, but then 1 day to compile to RISC-V? And that's kind of what we are trying to do with Gen AI, because Gen AI is evolving so fast that you will find that it's a surprisingly good second best option for compiler work. And what do I mean by this? I mean that as long as your code base is spec driven, that someone wrote a yellow paper for it, or even like a specification that is a blueprint in code, you're able to use Gen AI extremely easily to kind of adapt this blueprint in any language that you want. Why? Because you can test it on the specification. So you have this kind of like source of truth that will tell you, you have implemented correctly this blueprint. And I think this is what unlocks the potential of constraining Gen AI so that it doesn't hallucinate, but still leveraging the speed at which Cursor allows you to replicate a specification into an implementation. So that's the new choice kind of that we're exploring at Kakarot, because we're Cairo experts. So as I said, Cairo is a zkVM that's optimized for performance. Not yet privacy, mostly and uniquely performance. So how does it go? You just choose a ZK native instruction set. For us, it's Cairo. Then you pick a spec-driven mature code base. So the Ethereum virtual machine is mature because it's been implemented in 8 languages. And it has a yellow paper, which has tests edited by the Ethereum Foundation, and you have more than 200,000 tests, which means that whatever you do, as long as you pass those tests, you can call yourself an EVM. So So that's it. And the crux of what we're doing, trying to do at least to speed up our development, is to use AI to transpile existing work into a ZK DSL. And the way you get security is that you diff test every single entry point against the specification with fuzzing. But as you know, and I guess, who here has used AI, like an AI copilot in the last week? Who here uses GPT? Cursor? Okay. Well, I use Cursor as well, and I think it boosted the team's productivity. Like, we're 10 engineers in Paris. I think it 10x our productivity. But we do sometimes spend a couple of hours just trying to fix some hallucination. And I think you cannot trust Gen AI to produce production code. So what's the catch? How can you make it prod ready? Something that was generated very fast by AI. First of all, and as I mentioned, you always refer to the specification. Second of all, you need differential testing. What this means is that you take a block, let's take a block from Ethereum L1, you run it on the specification implementation, whether it is it's called ELS, it's a Python implementation, or a Geth, which is the Golang implementation of the Ethereum protocol execution layer. And you run it, and then you run it with yours. And as long as you fail the test, you start over, or like you better it. And that sounds awfully like reinforcement learning, or something that AI craves. It is a source of truth, something that someone knows is true, and as many tries as you want to make it work. Fuzz testing is a nice addition to just ensure completeness of tests, like for unitary functions. So I think we can go into our lessons learned. So our lessons is that we set out in end of December to rewrite from scratch the entire EVM specification in Cairo with Gen AI and with a very small team of like 2 people. So we call it ZK native because we are using a VM that is made for proving and that has no other use case than performant Stark generation, at least for now. We'll see how it evolves. And we used as a source of truth the ELS, which is the 1-year-old Ethereum Foundation repository that gives you, anyone, the source of truth on what Ethereum is in terms of code behavior. So what did we learn? Actually, we are using fuzz testing, and it's a very good tool. For those who don't know, it's called Hypothesis in Python. I know not many people use Python anymore, but in the Gen AI sphere, lots of people still use it. And it's perfect for unitary functions. So you're able to take one function from the spec, actually not state transition, but let's take, I don't know, operation add, operation multiply, and you are able to fuzz test the entire code production from AI in a very seamless way. You don't even have to write code for tests. You just write 2 lines of code that say, assert my function does the same thing as the spec function, and then you specify the type that you want it to behave on. So you say, for unsigned integer of up to 256 bits, which is the word size in Ethereum, try any number of values, like 15,000 values on the whole spectrum of values that are within 2 to the power of 256, and test it. And then we realized that this doesn't really work for specific functions that are extremely precise. So you cannot fuzz state transition, you cannot fuzz header validation, because it's too precise in terms of inputs and outputs that I expect. So for this, you need to rather use the specification. What we also noticed is that you must produce human-readable code. Why? Because this is not purely transpilation, or at least it's not compilation. It is translation of languages that is 10x the speed via AI. So what you're looking to do is do it once, and then start maintaining the repo you have obtained via this transformation that takes approximately 1 week to 1 month. And so what's nice is that you start from a high-level code base that can be proven with some performance. You translate it to an extremely performant proving language, and then you just go with it. You keep that, you maintain it as time goes, and you notice that 1, it's maintainable, and 2nd, it's more performant. So I would say that lessons learned, this approach is extremely, extremely good for when you have to prove infra. And what I mean by that is infra is usually code that is spec-driven, and that changes once every few months, but not once every few days. So the main thing that we learned is, we'll see with time, but this is not yet applicable to apps. which might need to be proven for some reasons, but this is more applicable to blockchain infra. So VMs, execution layers, consensus layers, bridge proofs, proof-based interop. And the last thing we learned is that when we started, it was Cloud 3.5, today is 3.7, and the speed at which things get better is actually scary. And the sizes of the context allow you to kind of feed the entire specification to AI, and it makes your job way easier. So we're going towards commoditization of code writing. I think this is how we see it. No one wants to write code, so people compile to RISC-V. And AI is getting so good that no one wants to write code and ask AI to write it. You cannot trust AI to write good code, so you check the specification that was written a long time ago that AI is behaving correctly. And there you go. You have this kind of way to write entire specification for blockchain in 2 months in a provable way. Oops, sorry. And this is what allowing us, at least Kakarot, to prove Ethereum in real time because Cairo is performant, but in a very novel way because we're producing code that has never been written before and that is completely like zk native, but also I would almost say sovereign in the sense that we are not reusing existing code bases as is. We're producing a new code base. And I think we'll see that this is extremely powerful for security because we're not, as an ecosystem, not putting our eggs into the same basket. We're not creating systemic risk of always using the same compiler like flow. And you will maybe see it later coming up in the next months, this idea of multi-proof and also a redundancy for clients. So we have a bit more time, but this was not the crux of the talk, so I will leave it at that. Yeah, I'm available for questions. And that's it. That's our socials. And I thank you for your attention. Can we take questions, or it's not even, because it's not so practical? At any rate, I think it's not so adapted.